So let's start by defining the quantity called momentum. As always, we like to start with a point particle. So suppose you have a point particle of mass m that's moving in space. At some instant in time, your mass m has linear velocity of this vector v. Then at that instant in time, the momentum of the particle can be defined as follows: p equal to mv. So obviously momentum is a vector. The magnitude of this momentum vector is the mass times the linear speed of the particle, and its direction is along the direction of motion of the particle or along the direction of velocity. So obviously the momentum of a particle can change with time, and Newton's second law tells us that for the momentum to change, you must apply a force on the particle, and the force applied on the particle is precisely the rate of change of momentum with time. What are the SI units of momentum? So momentum is very much a measurable quantity. The SI units are kg meter per second. Or another way you can put it is Newton seconds. Well, now that we have this form of Newton's second law, this most general F equal to dp by dt, what can we do with it? So we could try taking an antiderivative on both sides of this equation. We can try to integrate both sides from times t1 and t2. Doing that, when we try to integrate dp by dt with respect to time, by application of fundamental theorem of calculus, basically taking an antiderivative on a derivative, we just get p t2 minus pt1, which is the change in momentum between the times t2 and t1, right? So this quantity we can define as something called the impulse. So we have the following definition: impulse j equal to f dt, or the integration of dt between times t1 and t2, equal to, which you get by applying the fundamental theorem of calculus, the change in momentum between times t1 and t2. In other words, the impulse on a body between times t1 and t2 is the total change in momentum during this time. So j equal to the total change in momentum between t2 and t1, and we call j the impulse provided on the body between times t1 and t2. So notice that just by this definition, it's kind of clear that impulse is a vector quantity. So let's look at an example where we will evaluate impulse. So suppose we have a particle of mass 2 kilograms undergoing uniform circular motion of radius 2 meters and time period 4 seconds. So we've got this circle right here. The particles going in an anti-clockwise direction as shown, right? This 2 kilogram particle in a circle of radius 2 meters. So in the coordinate system indicated, which is as shown with the x and y axes, we want to find the impulse on the particle as it moves from A to B. So with anti-clockwise motion, let's say it starts at A and it moves at B. So we have here uniform circular motion. Let's start by finding out the linear velocity of the particle as it moves along this circle. Obviously the linear speed is going to stay constant because it's uniform circular motion. So we have v, which is the speed, should be given by this total circumference divided by the time taken to cover this whole circumference, which is 4 seconds. So we do have v equal to 2 pi times 2 meters over 4 seconds. So we have pi meters per second. Now let's say the particle is at position A here at time t1 and at position B at time t2. Because we have uniform circular motion, the speed of the particle stays the same as it moves along this circle at pi meters per second. So you might be tempted to say that the magnitude of the momentum here at A is just 2 kilograms times pi meter per second, and it's the same at B, so that there is no change in momentum, so that the impulse is 0. However, we have to understand that impulse is a vector quantity, and the momentum actually changes going from A to B because the direction of the momentum changes. The magnitude, of course, stays the same. So let's look at what that looks like. At time t1, the momentum vector would look like this. Of course, the particle is moving anti-clockwise, so the velocity points in this direction at time t1 when the particle is at A. So let's write this as p t1 equal to, so this is obviously a vector. We know that the magnitude of the momentum would be the mass, 2 kilograms, times the speed, pi meter per second. So we have pt1 has a magnitude of 2 pi, and how would we talk about the direction? So obviously the momentum points along the positive y-axis at time t1, so we just insert the unit vector j hat. So what about time t2? Again, the particle is moving anti-clockwise, so at the position B, the velocity vector would point like this. So the momentum vector would look like this, and we can write p t2. Of course, the magnitude of the momentum will not change. It will still be 2 pi. However, we see that the momentum vector points along the negative x-axis. To capture that direction, we need to multiply this with a minus I hat, so that the momentum becomes pt2 equal to minus I hat. So now the impulse between the time when it goes from A to B is simply given by j equal to p, the final momentum, minus the initial momentum, and we have to take into consideration the fact that these are vectors, and we do get minus 2 pi I hat minus 2 pi j hat. So it's important to understand that impulse is a vector quantity and treat it accordingly.